Look up toward the ceiling of almost any active manufacturing plant, and you will likely see fine dust drifting slowly through the air. It settles on the rafters, coats the top of the ductwork, and blends into the background of a humming, productive environment. Yet, if a single spark finds the right concentration of those suspended particles, that quiet environment will violently tear itself apart. Concrete silos split open, steel roofs peeling back. We need to ask why a material that seems completely inert while sitting on a table can suddenly flatten a city block. And more importantly, why do the explosions triggered by this dust kill workers in a very specific cascading pattern? This threat spans across nearly every sector of global manufacturing. In the American Midwest, researchers at Purdue University continually track facility-destroying blasts at corn mills and grain elevators. In Shanghai in 2023, a 3D printing lab working with aluminum alloy dust experienced a dual-stage explosion that fatally injured 2 workers. Any industrial process that grinds, mills, or transports dry materials is actively stripping those materials to their most volatile state. While the line workers operate the machinery below, a dormant explosive device is actively being constructed in the rafters directly above their heads. To understand the physics of these disasters, we start with the classic fire triangle, requiring 3 elements to ignite: fuel, heat, and oxygen. But an enclosed factory introduces 2 deadly new variables, expanding the triangle into the Combustible Dust Pentagon: dispersion and confinement. Milling a raw material into a fine powder massively increases its total surface area. When that high surface area particulate is dispersed into a cloud, oxygen instantly surrounds every single microscopic particle, creating an environment primed for a rapid, synchronized reaction. The cloud only becomes dangerous when it reaches its minimum explosible concentration, or MEC. This is the exact threshold metric where the ratio of suspended dust to oxygen creates a viable explosive mixture. Once a dust cloud crosses that MEC threshold inside a confined building, it ceases to behave like a solid material. It acts exactly like a highly explosive gas. The destruction starts small. A primary explosion occurs inside a confined piece of equipment. This initial blast generates a high-pressure shockwave that slams into overhead structures, violently shaking loose accumulated dust. Then, the flame front catches up, triggering a massive secondary explosion. This is a deflagration, not a detonation. High-order explosives like TNT undergo detonation, producing a supersonic shockwave. Dust explosions are deflagrations, meaning the reaction front travels slower than the speed of sound. They generate a massive volume of expanding gas and a violent rush of air called a blast wind. That specific combination of pressure and wind inflicts severe trauma. The sudden overpressurization causes primary barotrauma, rupturing the lungs' air-filled cavities. The blast wind creates secondary injuries, shredding the environment into high-velocity shrapnel, and tertiary injuries from physical impacts. The localized mechanical failure that starts the fire is rarely the fatal event. The workers are killed by the recursive secondary blast, fueled entirely by the dust accumulating in their own facility. Following these events, investigators from the Chemical Safety Board, or CSB, the independent federal agency that investigates industrial chemical accidents, consistently find that these disasters are the predictable result of ignored warning signs. In 2010, the AL Solutions facility in West Virginia was processing titanium and zirconium scrap metal. Employees had noted mechanical problems with a blender in the days prior. The friction from a broken paddle inside that blender ignited the highly reactive metal dust. 3 workers died in the ensuing blast. At the U.S. ink plant in New Jersey, management installed a new dust collector without obtaining the required building or fire permits. A highly flammable mixture of carbon black dust and condensing oil vapors accumulated inside the ductwork. It spontaneously ignited, causing a flash fire that severely burned 7 workers. Investigators measure the risk of secondary explosions using a strict metric, the 1/32nd inch rule. A layer of dust just 1/32nd of an inch thick, roughly the thickness of a standard paperclip, is enough to create a lethal, facility-destroying cloud if it is knocked into the air. Equipment will eventually break down. Bearings will fail, and sparks will happen, but that mechanical failure only provides the ignition. It is the failure to clean up that paperclip thick layer of dust that actually builds the bomb. To dismantle this threat, federal guidelines rely on strict regulatory frameworks. OSHA's Process Safety Management Standard, known as 29 CFR 1910.191, governs the handling of highly hazardous chemicals. Additionally, the new NFPA 660 standard unifies the rules for combustible dust, requiring rigorous laboratory testing to determine exact explosion pressures and minimum ignition energies. Under these rules, employers must conduct thorough process hazard analyses to identify hidden accumulation zones. They must maintain ventilation equipment, issue strict hot work permits, and implement aggressive housekeeping schedules to control fugitive dust. On the floor, workers must immediately report overhead dust buildup to management. They need to secure any equipment that is grinding or producing friction, and they must know the exact evacuation routes the moment a primary deflagration is suspected. The factory floor does not have to open up beneath the people working on it. A layer of industrial dust is completely harmless, but only if we refuse to ever let it accumulate. If you found this breakdown helpful, make sure to subscribe to HSEstudy. We regularly explore the science of workplace safety and provide the insights you need to stay OSHA compliant and keep your facility secure.